we're going to flip now from thermochemistry to thermodynamics. In thermochemistry, we talked about enthalpy, and here, through Big Idea 5, we are going to link it to entropy and whether a reaction is thermodynamically favorable, also known as spontaneous, and for those of you in or taking AP Bio, also known as exergonic. So we're going to link enthalpy now with entropy, a measure of disorder, and free energy to determine if a reaction is thermodynamically favorable. And you'll see thermodynamically favorable in red a lot because in older textbooks it's listed as spontaneous. In your POGL packets it will still say spontaneous, but on your AP exam it's going to say thermodynamically favorable. Thermodynamics looks at the relationship between heat and work, and that's what we're going to do here. When a reaction occurs without any assistance, we say that it's thermodynamically favorable or spontaneous. To determine if a reaction is thermodynamically favorable, we're going to examine both the enthalpy and the entropy. Entropy is a measure of disorder in a system, and disorder is a good thing in chemistry, even though it's a disaster in some of your rooms at home. Entropy is a measure of how energy is spread out among atoms and molecules of a system. The more spread out it is, the greater the entropy, the more it will feed into thermodynamic favorability. So free energy is going to relate enthalpy and entropy together, and we'll talk about that next time. If a forward reaction is thermodynamically favorable, the reverse process is not, and we'll come back to that later on. The other distinction I want to make sure is clear is that when you talk about whether a reaction is going to occur, you need to consider two criteria. The first is the reaction kinetically favorable? We talked about kinetics already. Does the reaction occur fast enough to be kinetically favorable? Is the activation energy overcome? If a reaction is not kinetically favorable, what you're primarily looking at is a very high activation energy or perhaps an inhibitor resulting in an alternative pathway with a higher activation energy than without the inhibitor. The other criterion that must be met is whether the reaction is thermodynamically favorable. Does it occur without any assistance? For a reaction to occur, it must be both kinetically and thermodynamically favorable. Shown here is the reaction profile we've looked at previously, where you're going from reactant to product and you're following the pathway along the way. Is this reaction endo or exothermic? Exothermic is correct with the negative delta H. Your starting point and your finishing point focuses on the thermodynamics. Keep in mind that enthalpy is a state function. You will see that entropy and free energy are as well, depending only on the end and the beginning. The pathway you take is where the kinetics come in. So the kinetics region versus the thermodynamics region. Entropy is it's a relatively backward concept because here disorder is a good thing. And in this case, when you have disorder in a system, you're talking about positive entropy. Disorder helps thermodynamic favorability, but it's not the only factor that determines thermodynamic favorability. Entropy is a measure of disorder in the system, and it's roughly equivalent to the degree of disorder in the system. The greater the number of particle configurations, the greater the disorder. Now your textbook goes into a lot of probability and statistic variables on this. I think it may be a bit much for you, but if you have 4 particles here and you want to consider all the different ways that they can be arranged, not only with 3 and 1, but also the exact location of those particular particles, there are a number of ways in which they can be arranged. The more disorder you have in the system, the greater the entropy. What you also find is that the more atoms in a molecule, the greater the disorder. And you'll see this in a few minutes in your notes, but I'll mention it here. If you're comparing the entropy of carbon monoxide versus carbon dioxide, or let's say phosphorus trichloride versus phosphorus pentachloride, you find that in each case, the molecule with more atoms will have greater disorder. You can also predict whether a reaction is showing disorder or order, and we'll get to that here. Entropy, as I mentioned, is a state function, and as a result, it depends only on the beginning and the end. And very similarly to the way that you calculated the delta H for a reaction, where you did products minus reactants of the delta H's of formation, you can do it very similarly to calculate delta S. We'll be looking at that in a few minutes. But the fact that it's a state function says you can do products minus reactants here, and you'll see it for free energy as well. You will see an increase in entropy for these processes. A solid melts to form a liquid. Which state has greater order, a solid or a liquid? Solid. Okay? So much greater order in a solid. So as a solid melts, you get more disorder, the entropy increases. When you vaporize a substance, the entropy increases. If you dissolve solid salt in water, entropy increases. The molecules now, or in this particular instance, if you had something like salt, the ions will break apart and they will become hydrated.
Is there a larger change in entropy from solid to liquid or gas?
What do you think?
Probably from solid to liquid.
Why?
Because it's like really ordered before.
But which one breaks all the IMFs?
Liquid, gas.
So what are you going to guess?
Probably larger change in entropy from liquid to gas.
Definitely, and that's due to the delta H of vaporization being greater than a corresponding delta H of fusion. Yep, and just think your way through it, and that's how you're going to answer it. When you see an increase in the number of molecules of gas, you'll have an increase in entropy. I'll show you an example of that in just a minute. When you heat a substance, the particles move faster, and as a result, the entropy will increase. If you allow an ideal gas to expand by opening up a stopcock in a bulb-type apparatus that we've looked at previously, greater disorder here than here. So in each of the following, we want to predict whether you get an increase or decrease in entropy. First example, you've got gases on the left and a solid on the right. Which one's more ordered? Definitely the product, because it's a solid, so this would be a decrease in entropy. Decomposition of potassium chlorate, you've got a solid on the left, and you've got solids and gases on the right. That would be an increase in entropy. Tough to predict here. You've got carbon monoxide and water. Both are gases. You've got carbon dioxide and hydrogen. Both are gases. How many moles of gas do you have on the left? 2. How many moles of gas on the right?
2.
You could never, at your level, predict this. You would need to calculate delta S, which we'll do in a minute. Also difficult to predict on another level because, as we said previously, if you compared these two, you would predict that carbon dioxide would have greater entropy because it has more atoms. And what would you predict would have greater entropy here?
H2O.
And let's see if we're right. If we look, and we're looking at the last column now.
Can't see.
Can't see? If we were to look at hydrogen, entropy of 130 joules per mole Kelvin, different unit for entropy, we'll get there in a minute, versus water in the gaseous state, you do see greater entropy, higher, greater positive value, if you will. And let's check the carbon monoxide versus the carbon dioxide, and again, it does hold true. But you have that on both sides, so if you consider the equation, very difficult to predict. So you'd never be asked to predict one like that. But look at the last example. You have 2 moles of gaseous reactant, and how many moles of gaseous product? 3. You want to babysit for 2 kids or 3 kids? What's more work? 3 is so much more work. The house is going to be far nuttier. You should get paid more. As a result, you'll see an increase in entropy in this reaction because, be careful of your justification, you have a greater number of moles of product, 3, versus 2 moles of gaseous reactant. So the number of moles of gaseous product, which is 3, is greater than the number of moles of gaseous reactant. When you are comparing moles like that, just do it for a gas. Stay away from the liquid-solid comparison. Anytime you go from gas to liquid, you're getting more ordered. Anytime you're going from liquid to solid, you also should be getting more ordered.
Could you base the change in entropy based on the reaction type? Like decomp or synthesis?
I'd say in most instances, yes. Decomp should result in disorder, and synthesis should result in order.
So like for the last one, could you use that rule?
Most likely. I don't want to say always because I know there'll be one that will come back and get us. So most likely. And it's an excellent
Observation.
conceptual observation. Absolutely. You got it. Good job. I like that. And then we've got synthesis up here, right? Woohoo. But be careful because whereas most decomposition reactions are endothermic, not all are. Combustion's always exothermic. Most synthesis reactions are exo, but not all. So just be careful with the always. You can calculate entropy from Q. I don't really see where we're going to be asked to do that, so I don't really want to get into it, and the relationship's a little tricky. But you know that as you increase temperature, what happens to particle movement? It increases, and as you increase particle movement, what's going to happen to the entropy? It's going to increase as well, more and more disorder. But I don't really feel that you will be required to know this, so let's not. The other thing I want to take a look at is just an example of the standard molar entropies. Again, this is grossly similar to what we saw with enthalpy. It requires some practice. We'll take one here together, but you need more on your own. Standard molar entropy, the entropy of 1 mole of a substance in its standard state. The third law of thermodynamics says that the entropy of a pure, perfect crystal is 0 at 0 Kelvin. Why would that be? At 0 Kelvin, does anything move?
No.
Not atoms or molecules, and as a result, the entropy will be 0. One thing I want you to see, because I don't want you to make the assumption, if we look at entropy values, whereas delta H is of formation for diatomic elements as well as elements in their standard state, and that would be diatomic elements in their standard state are 0, the entropies are not 0. So if they ask you to calculate the entropy of oxygen gas, it's not 0. Be careful. And this already, Maddie had asked this question. She sort of beat me to it. We worked through it, and I've got it for you here. If you look at standard molar entropies of substances during melting and evaporation, you'll see an increase in entropy for both. But as we discussed already, there's a sharper increase when you boil. And why is that? You break all the IMFs. You got it. I already mentioned to you that the entropy of a substance with more atoms in it would be greater than a corresponding one. Entropy, abbreviated with an S. Values are provided here. Note the unit of joules per mole Kelvin. The unit will become critical a little later in the chapter. You'll see it today. Entropy is an extensive property, so it does depend on the amount of substance. You'll have to take the number of moles into account. Entropy can be calculated similarly to the way we calculated enthalpy. If we wanted to calculate the standard molar entropy in this particular